All right, so today we have Christian Copetti, who will tell us about duality preserving RG flows in 4D supersymmetric theories. Take it away.
Okay, thanks a lot for the invitation. So the idea today is the following. So what I want to describe is how some special symmetry, namely these duality symmetries, which are some kind of generalized symmetries, can be preserved in 4D theories which have supersymmetry, and what are the conclusions that you can, what is the information that you gain about the low energy phases of such theories. And most application will be on gapped phases, so gapped vacua. And we are currently working on trying to understand gapless phases. I don't know if we will be able to, but we're trying. And we're also trying to look at RG flows which do not preserve SUSY, but preserve these symmetries. So now I will try to introduce the stuff. So most of the talk is based on this. Can you see my pointer? I hope so.
Yes.
No? Okay. Most of the talk will be based on this work of last year, but there are some parts which I will mention which come from other papers which I recently have written. So I will start with an example in 2 dimensions, which will have all the features that will appear in 4D, so we can make some analogy. It will be maybe easier for people who are not in this topic to follow. So the plan is the following. We start with a 2D example of RG flows which preserve some generalized symmetry and what are the implications of such RG flows. Then we go to 4 dimension, we study the example of n equal to 4 and some well-known RG flows, and we try to understand if we can preserve such duality symmetry and what are the implications. And then I will try to talk about some other cases that you can work out. So we'll talk about some n equal to 1 cases, and in particular about the Klebanov-Witten SCFT. It's possible to do this in many other examples, but we didn't work them out. But I think it's straightforward to generalize in many ways. Okay, so let us start. First, in 2D. So most of the material is kind of well known. I'm just rephrasing it in a way that will be useful for my rest of the presentation. So the example is always the standard one, which is the Ising CFT. This is the table of the primaries. So these are the primaries of the Ising CFT. And these are the symmetry operators that you have. So these are topological line operators for this identity. This is the Z2 symmetry of Ising. And this is a special symmetry, which is the Kramers-Vanier duality. So in all the diagonal CFTs, the spectrum of these line operators is isomorphic to that of primaries. So you can always draw this kind of table. And they just give you the way in which these line operators fuse among themselves. So, of course, eta squared is 1, the Z2 generator. Then this Kramers-Vanier duality absorbs the eta line. And then you have this weird rule that n squared is 1 plus eta. This tells you that n has no inverse, and this is why people call this non-invertible symmetry usually. So, okay, I decided not to give an introduction about symmetry as topological operators because I think people have already seen this like a million times and it's starting to get a bit too much. So I'm just gonna give the example instead. You can write down what is the action of the symmetry operators on the primaries. So for example, the epsilon operator is neutral under Z2, the sigma operator is charged under Z2, and then there is the action of the n line. So the n line gives charge -1 to epsilon and maps the sigma operator into not into a local operator, but into a twisted sector field. So you see this is the eta line. This is mu, is the lowest line field in the twisted sector. It has the same dimension of sigma, is 116, 116, 2. But this is not a local operator, so let me stress this. This is like the important feature of the non-invertible symmetry in this case. Okay. So let us try to understand how this acts on gapped vacua now. So what we can do in the Ising is to deform from the CFT point by turning on the epsilon, for example. And so this is what you do. The epsilon is charged under n, so it breaks it, of course. And there are two phases, no? There is a high temperature phase, which is the disordered phase, the usual one, in which there is no magnetization, and there is one vacuum. And there is the low temperature phase, which is the ordered one, in which you have an ordered parameter, and you have two vacua. In both the cases, the Z2 symmetry is unbroken because epsilon was neutral. And okay, in the modern language, instead of talking about one or two vacua, we can associate a TQFT to the low energy theory. So in the case of the disordered phase, we would associate a trivial SPT. The partition function is just one, so it's the most trivial thing you can imagine, but I will give it a name nonetheless. While to the ordered phase, which is an ordered phase for the Z2 symmetry, we associate a Z2 gauge theory. So these two vacua are exchanged by the Z2 line in the gauge theory. And the claim of Kramer's vanilla duality, so high low temperature duality, is that the N line maps the disordered phase into the ordered phase. So in some sense, it should map this trivial theory, which has only one vacuum, into two vacua. And now we try to understand how this works. Okay? Are there any questions on the setup? Okay, so let me go on. So another description of this N defect is the following. One can notice that if you gauge the Z2 symmetry in Ising, you go back to Ising itself. This is just because when you gauge Z2, the sigma operator disappears, which is charge under Z2, becomes a twisted sector, but the mu operator, which has the same weight, becomes a local operator. So the spectrum of primary is unchanged. Epsilon remains there. So if you gauge Z2, you still remain in Ising, but in a different duality frame if you want, because now you have the mu operator instead of the sigma. It's a bit of a subtlety, but it will be important in 4D. So what you can do is you can gauge in null space. So here we gauge the Z2 symmetry in null space. We understand that the theory is the same. So I will put this dashed line to say that I do this trivial operation of doing Kramer's vanilla duality, which doesn't do anything. It's just describing it in a different duality frame. And I go back to the starting point. So this operation is topological. So I can push the dashed line onto this null space gauging boundary, and I define a topological defect. And it's possible to show that this is exactly the N line, the duality line of the Ising CFT. So this description is more useful for some purposes. In particular, you can show the following. So now let me give you the partition functions of these two vacua that we described before. So the partition function of the trivial SPT, A is just a Z2 gauge field because you have a Z2 symmetry. We can turn on a gauge field. As always, it's an element of H1, X, Z2. The trivial theory has partition function 1. And the Z2 gauge theory has a partition function, a delta function. Okay, this is quite trivial. But now, if you act with the duality defect, you know to act. It's just gauging the symmetry. So it's just a Fourier transform. So if you Fourier transform 1, you get a delta function. And if you Fourier transform a delta function, you get 1. And this shows you that the duality line eta maps the trivial phase with one vacuum to a non-trivial phase in which the Z2 symmetry is spontaneously broken and it has two vacua. Okay? This is an important point. So when you have these non-invertible symmetries, what can happen is that an ordered phase can become a disordered phase, which cannot happen with normal symmetries, like with groups. And this is because the ordered parameter, which in this case you can think of essentially the sigma operator, gets mapped to a non-local operator by the symmetry. So the order is not anymore in the normal Hilbert space, but is in the twisted Hilbert space. So you won't see any traditional order parameter after acting with the symmetry. And this is one of the important physical consequences of having non-invertible symmetries. Okay. So any questions on this? So this is also a good time to like, because then it will be always based on this idea. So, okay, let's go on. So now we go to the next step, which is to make duality preserving RG flows, no? So in Ising, there is none. You can only turn on epsilon, and epsilon breaks the duality line. But you can go to the next minimal model, which is a three-critical Ising, C equals 7/10. Again, it has a table of primaries, here more. But you see these ones, these are the topological lines. So you can forget about the last three. We don't need them. But you see that these three have these names because they're the same as the ones of the Ising CFT. Okay? And in particular, there is one operator, which is this epsilon prime operator, which has dimension 6/5, so it's a relevant operator, which preserves both the eta defect and the n defect. So what I mean is that is neutral under n and is neutral under eta. So now what we can do is start in the UV from the critical Ising, and we turn on this deformation, lambda times epsilon prime. This preserves this subcategory of symmetry. This symmetry is preserved. This part is broken, but we don't care. But this is preserved. Okay, all along at any energy scale, this is there. And you can ask, what is the RG flow? No, this is a well-known RG flow from maybe the 70s or 80s. People could do it on the lattice essentially. And there are two possibilities. So if lambda says positive, I mean, lambda is not very well defined. You have to tell me how you normalize epsilon prime. But let's say for lambda positive, you flow to the Ising model, which makes sense. It has less central charge, it has the same symmetry. But if lambda is negative, you flow to a gap theory. And it was known that this theory has three vacua. Now, if you just find the result, you say, why three vacua? No? Why not one? Why not two? And now we know because we have the duality symmetry. So, by the way, let me also remark there are other flows within minimal models. In particular, you can always turn on this 513 operator, which is relevant in all the minimal models. And you can make similar remarks with the two signs. There is a gap phase, and it has many vacua which are fixed by the symmetry. But just to tell you that it's not only this case of the Ising, but this is the simplest. So I think it's a good example to show. Okay, so why three vacua? Okay, we have seen it already. So we can think of them as a trivial SPT and the Z2 gauge theory. And they are permuted by the duality symmetry. So the duality symmetry in this phase is spontaneously broken. Okay? Since it's not, and if you do a bit of math, so this is maybe not the obvious result, but this number is the minimum one which is allowed on which this symmetry can act. So there is no single vacuum because this only this theory, and there is no way to have only two because it's just this theory and they get exchanged. Actually, there's a bit of subtlety here too. If you work on spin manifolds, there is a way to get around this, but I will not say more. But there is some subtlety about spin structures here. But in this case, if you don't care, this is the situation. And you can ask, is there something that tells us that this symmetry cannot be preserved in the infrared? And it turns out that this thing that you can have at least three vacua in the infrared is an anomaly for the non-invertible symmetry eta, sorry, n. So this is the usual thing that if you have an anomaly and you try to flow to a gap theory, you cannot have a gap theory which preserves the symmetry. It must be spontaneously broken by 't Hooft anomaly matching. And this is a similar story, but for generalized symmetry, for non-invertible symmetries. Okay, so let me just restate what we want to bring to higher dimensions from this story. So first thing is that non-invertible symmetries can map genuine or local operators into non-genuine ones. So there can be operators which are attached to lines. Okay. The second is that there is a special family that we will focus on, which are these duality defects. And in all dimensions, they are constructed in the same way. they come from noticing that when you have an abelian symmetry, it will be some higher form symmetry in higher dimension, and you gauge it, you can go back to the same theory, but in a different duality frame. And this will be apparent in n equal to 4. In this example, this symmetry A is Z2, and the duality we use is the Kramers-Weyl duality. Let me stress again, when you flow to gapped vacua, the structure of this vacua is strongly constrained by this symmetry. It's much more constraining than a normal group. And these patterns, the fact that you have non-trivial patterns appearing, usually encode anomalies of these symmetries. Okay. Finally, again, a physical consequence of this structure is that when the symmetry is spontaneously broken, you can have phases in which domain walls, which are implementing these symmetries, map an ordered phase, which has a local order parameter, to a disordered phase, which there is no such ordered parameter. And if you see that this happens at some point, you should think of this, that this is the smoking gun of spontaneous breaking of this non-invertible symmetry. Okay, any questions?
Yes, I have a question. So when you say that there are anomalies of these non-invertible symmetries, is there a more fundamental concept of what is such an anomaly that then you see that it's have these constraints on the infrared gapless phases, or are you using the infrared gapless phases as the definition of this is an anomaly for the non-invertible?
Well, this is a bit of an open question. So one way in which people, so for the normal symmetry, there are two concepts of anomaly which coincide. You can either have the obstruction to an SPT, or you can have the obstruction to gauging the symmetry. And the two things coincide. For non-invertible symmetry, usually they do not. And many people use this obstruction to have an SPT as the condition to be anomalous, and that's called the presence of a fiber factor. But for this kind of symmetry, these duality symmetries, you can show that they are equivalent. So it's, in some sense, they're equivalent. So when you have this invariant theory, you can also gauge the duality defect, actually, together with some of these other zero-form symmetry defects. But so here's another technical thing, though. So it's not, there is no simple characterization that I know.
I see. So here, gauging the non-invertible means summing over all the possible network of defects?
Yes, you have to choose a special network, essentially, which contains this defect and special junctions in this network. That's called the symmetric Frobenius algebra in 2D. And if you do that, if you find this, then you can sum over, and it's like gauging. This is the closest thing to what usually you call gauging. But it's not, I mean, it's not clear which name you want to give to the fact that these anomalies. In general, I think the consensus is towards looking at SPTs. Okay.
Okay. Thank you very much.
Okay. Other questions? Okay. So now let's go to 4 dimensions. So we talk about n equal to 4 super Young Mills. So again, we will do the same things step by step. So in this case, we will just consider the gauge algebra to be SUN. You can do it in many other cases. It's just a bit more technical. So for us, we'll do SUN, and in particular, we will mostly do SU2. You can do the higher ones, and they are quite simple. They are in the paper. But you don't learn much more things. So I think SU2, SU3 is already enough. So here the duality group, as is well known, is SL2Z. Okay, if you are very picky, it's the metaplectic group, because S to the 4th is fermion parity. And it's known, has been known for a long time how this acts on the various observables of the theory. In particular, it acts on the complexified gauge coupling tau, as follows. But it also acts on the supercharges. This will be important for us in the following way. And you can check, okay, so this was known since Kapustin and Witten, and you can essentially compute this on the Coulomb branch. So it's kind of a simple computation in some sense. It's nice. But what is important is that the generators of the duality group also change the gauge group. They don't change the gauge algebra in this case, but they change the gauge group, which I will refer to as global variant. So for SU2, there are 3. And for example, the action is as follows. So you have SU2, SO3 plus, which is just gauging the one-form symmetry, and SO3 minus, which is gauging the one-form symmetry with a discrete torsion. And here I put which line is the local line, the line which is a genuine object, is not attached to any surface. So in SO2 you have Wilson lines, and this is invariant under T, but is mapped to SO3 plus by S. In SO3 plus you have the Toft line as genuine objects, and in SO3 minus you have the dion, which I denote as WT. So I'm suppressing the representation, but in general, if you will have always representations which are of anality n, those are unconstrained, but those which have less anality have to be of this form. Okay, it's kind of well-known fact. And notice that this SO3 minus is invariant under S. This will be important in the rest of the section. Okay, so as a symmetry, now we consider the one-form symmetry. So before we had the Z2 0 form, now we have Z2 1 form because we're in 4D. And okay, this acts on Wilson lines in the SUN description by linking. So this is a two surface in reality, but I cannot draw it, so it's a line. And if you take a representation of anality K, so it has K boxes, modulo N, you get this phase once you bring the surface around. Okay, so it's just a Zn one-form symmetry. If you have this Zn one-form symmetry, you can define two topological manipulations, which are the equivalent of the gauging we had before. Remember, before we had to gauge on half space, so now we have two guys that we can do, which I call sigma and tau with obvious notation. So sigma is gauging. So again, you sum over the gauge field for a one-form symmetry, which is in H2. And then you add the minimal coupling to the new gauge field. It's just Fourier transform. And this tau that you didn't have in the two-dimensional case is to stack an SPT to the bulk. So the SPT for the one-form symmetry is just generated by this Pontryagin square operation, which you should think of as essentially B wedge B. So this is enough. And you can stack this. There are some subtleties how it works on spin versus non-spin manifolds, and I will tell you when they come in. But if you work on spin manifolds, they form the group, the sigma and tau form a group because they map theories with one-form symmetry to theories with one-form symmetry, and the group is SL2Zn. Okay, since you have some gauging operation, they also act on the global structure of the gauge group. And for example, for SU2, you see it's like the mapping we had before. If you do sigma, you go from SU2 to SU3 plus. Sigma tau brings you like this. I think it's the opposite way the other. I think I got it wrong. This should go this way, this should go this way, this should go this way. But okay, sigma tau I think maps this, and then this, and then this. But, okay, sorry for the typo. But it has also an action on this global variance. So the important thing is the following. And this SO3 is invariant under sigma, SO3 minus. It's the same action as in the slide before. So there is this triplet under sigma tau, and there is a singlet and a doublet under sigma. This we will need after. Okay. Any questions on this part? Okay, let's move on. This is kind of standard at this point, but I wanted to introduce it. So again, now we have to find some special. So if we now gauge this symmetry, we can go to another global variant of the gauge group, and we want to use duality to go back. But we can go back only if we fix a special place in the modular in the conformal manifold, so that we stay there when we use duality. This we didn't have in 2D. But here it amounts to fix tau equal I to have a duality defect. So we act with S, or we can fix tau equal to pi over 3 and act with ST. And okay, and you do the same. So you gauge in our space, you go to SU3 plus at tau equals I, and you use S, and then you shrink this, and you get a duality defect. Or you can gauge with this discrete torsion tau, you go to SO3 minus, you do ST, and you go back. So this is just the same construction as in 2D, but now we have this small fact that we have to fix where we are in the conformal manifold. Okay. Now we can also write down what is the symmetry algebra as we did before. So this is just I'm writing line operators as points, so they come out in this direction, just to be a bit economical. This is just the action, the one from symmetry of the Wilson line. Then we have the duality symmetry, which does the same as before. It maps a local line, which is a Wilson line, into a Toft line. But the Toft line in the SUN gauge theory is not a genuine line, it's the end of a one from symmetry surface. And the fact that it's the end of the one from symmetry surface justifies that the two have non-trivial Dirac pairing, so they are mutually non-local. And finally, you can fuse this eta surface to the D surface, and you get the D surface. This is essentially the algebra we had before in 2D. And again, you can do the same reasoning. So you can now study gapped phases which preserve the one form symmetry. Okay, so before we have zero form symmetry, now we have one form symmetry. So there is also here a confined phase, which the Wilson line has area law, and is described by a trivial SPT, as before equal SPT 0. And there is a deconfined phase in which the Wilson line has perimeter law, or if you reduce on the S1, it has eigenvalues plus or minus 1. And this is described by a Z2 gauge theory, but now is a one-form symmetry gauge theory. So the partition function is a delta of a two-form instead of a one-form gauge field. But it's the same thing as before. And again, using the description based on the half gauging, you can, by Fourier transform, you can show that these two are mapped into each other. So the symmetry maps a confined phase into a deconfined phase, and vice versa, which is kind of the important point here. But if I have a spin manifold, there is one more SPT. So if you want this SPT corresponded to having Toft lines with perimeter laws, but are not local operators. But there is one in which dions have perimeter law, which I call SPT1. It's just stuck in this SPT, which is P of B. And you can show by essentially doing a Gauss sum that this is invariant under the duality symmetry. Remember, it's the same as before. There was this global variant which was invariant, and you find an SPT which behaves in the same way. So the fact that this theory exists actually tells you that this duality symmetry is not anomalous if you have a spin manifold for n equal to 2, so for the SU2. In general, it will be different. And again, you can write down the full action on vacua under these transformations. So this is the gauge theory, and this is SPT1. So you see sigma as one singlet and one doublet, as before in the Ising model. Then you have sigma tau, which is a triality defect, which has a full orbit. So you conclude that the triality symmetry is anomalous, while the duality symmetry is not anomalous. Okay? And okay, now that we have done this, we do the same as before, and we think about deformations which can preserve the symmetry. So now we start from n equal to 4 with the form, and we try to preserve the duality or triality symmetry and see what happens. Okay, so the first thing that you do is that you turn on a quadratic superpotential. That's the simplest deformation. And this is well known and well studied. So the only subtle thing, the scalar field is neutral under the duality symmetry if we choose it in a certain way. But if you want the superspace coordinates transform because the Q transform, so when you integrate the superpotential, you get a phase, which is here 2 pi I over k. So k is 4 for duality and 3 for triality. Just was to write only one equation. So to preserve the symmetry, you need to do some compensating as symmetry transformation, which cancels this phase. But you're in luck because this breaks always a superconformal symmetry, since the deformation is relevant, and you can use it to rotate back and cancel the phase. So once you've done this, I mean, it's just a technical thing, you can define a new duality defect, which I call the twiddle. It's the same one as before, but it's composed with an discrete L-symmetry notation. And this is preserved along the LG flow. So this leaves the superpotential invariant. Okay? Yeah, of course, you have to start the LG flow at the special values of tau in which the duality was present. So you start from I or 2 pi over 3, you turn on the quadratic superpotential, you flow down, and you are assured that you will have this symmetry in the IR. So these flows are very well known, and there are 3 cases essentially that you can study. So one is when you have only one non-zero mass, then you go to n equal 1 SCFT with quadratic superpotential. If you have 2 non-zero masses, you have the n equal 2 star tier, which has a Coulomb branch of vacua. And if you have 3 non-zero masses, you have the n equal 1 star deformation, which goes to gap vacua. It also has Coulomb vacua, but I will say something about the Coulomb vacua only if we have time. In the first case, we can just say that this theory in some point of the n equal 1 conformal manifold has a non-invertible symmetry. This is what we have shown. But we don't know of the implication of this for the dynamics. We said to know how to attack this problem yet. In the second case, you can kind of look at the results, for example, of Donagi and Witten and try to understand the action of duality on the Coulomb branch. And it's not very interesting, I would say. But the third case is more interesting, and we will talk about this for the rest of this part of the talk. Okay? Any questions on the ideas here?
Yeah, maybe I can ask a quick question.
Yeah.
So you kind of made an assumption somewhere, I think, that the one form symmetry was not anomalous, so that you can define this one form gauging in any case.
Yes, you need it to be non-anomalous, otherwise you don't have this symmetry.
Right. But is there then an interesting consequence? So if this symmetry is anomalous, and then you don't have the defect DS, does that tell you something interesting about the vacuum structure in those cases?
I mean, if the one form symmetry is anomalous, you don't have the S that you cannot construct, but the vacua will be constrained by the anomaly of the one form symmetry. So, for example, you cannot have the SPT, you can have the confining phase if you have a pure anomaly. But in 4D, there are no pure anomalies for the one form symmetry, I think. So it's okay.
I see. But for any
you have mixed ones.
For SU4, you have anomalies for the one form symmetry sometimes.
There is one when you go to not SU4, but when you gauge Z2, because you have Z2 times Z2, and then you have an anomaly. Yeah, that's true. So in that case, what happens is that if you go to that frame, the duality symmetry becomes invertible, and you have a mixed anomaly. And this is another. So this is all tied up. So what happens always, just to answer the question a bit, is that when the duality symmetry is non-anomalous, say in the SUN description, there is always another description that you obtain by discrete gauging, which the duality symmetry is invertible, and there is a mixed anomaly in the one form symmetry. Sorry, not the one form symmetry, but between the zero form symmetry, the duality symmetry, and the one form symmetry. But there can be more. There can be also one form symmetry anomalies like this. So the Z2 times Z2 is a bit more tricky. In the paper we treat it. Here we just show a table for the Z4, I mean the SU4, but you can also do SU4 mod Z2. Yes, thanks.
Okay, cool. Thank you.
Okay, so let's see how much time I have. Okay, I'm going very well, so I can go not fast. Okay. So now I'm going to focus on this n equal 1 star deformation. So this is all well known. So my point is just to show how the symmetry emerges in this description, that it justifies some kind of claims in the literature. Okay. So first, let me just remind how the vacua of this n equal 1 star description are obtained for SUN. So classically, you have to just solve the F-term equation. So you just write down this SU2 algebra. And a classical vacua is determined by a partition of n, which is essentially embedding SU2 algebra, SU2 representation into the scalar fields phi, no? And the sum over this must be, or dimension must be n. Okay? Then the rules are simple. So when you embed the biggest possible representation, you have an X phase, which is always there. This is a phase in which the one from symmetry is completely spontaneously broken, which corresponds, if you want, to the Z-gauge theory. If you have R blocks which have the same size, then there is an unhixed SUR gauge group. And this at the quantum level confines and gives rise to R vacua. So every time you have certain numbers of blocks, you have multiple vacua, which I label in this way. So H is just X confined, R is the number of which I have, and this is the label of the vacuum. So for example, you always have the embedding of the trivial representation and time. This corresponds to no Xing, and the theory is like pure n equal to 1, essentially it confines, and you have n confining vacua. Okay? But then there are these intermediate things. And when you have sets of blocks with different dimensions, you also have unbroken U1s and unhixed U1s, and then you have a Coulomb vacua. So maybe since I have a bit of time, we will comment about the implication of duality symmetry on the Coulomb vacua. You can also say something similar, but these are not gap vacua. Okay. So to this gap vacua that I described, you can associate TQFTs as we did before. So we really know a bit how the game goes. So in the X vacuum, the one from symmetry is completely broken, and you associate a Z-gauge theory. Okay. If you have a purely confining vacua, the one from symmetry is completely preserved, and you have to associate an SPT, which is this exponential of the Pontryagin square. And there is like a standard choice, which matches what you get in n equal 1, for example, but it's always a choice of UV counterterm if you want, which for which the K vacuum is the SPT minus K. So it's e to the minus 2 pi I K PDB, P of B. Okay, this is the choice we use. It's a counterterm if you want. And if you have this other vacuum, this mixed one is a bit more complicated, but you can describe them as a TQFT in which there is a Z n over R, which is spontaneously broken, is like a gauge theory, and you stack on top of it an SPT. So it has two parts. But we will not use the explicit expression. You can associate this TQFT, and you can check they are consistent with all the definitions, with all the action of duality. So again, now we want to look at the action of these duality defects and see if they match the action with the sigma and tau, this discrete gauging, no? So in practice, there are two ways to describe this action. One is that in each vacuum, you have a line operator which condenses, it has perimeter low, and then the element of the S-duality group maps different condensed lines. So this gives you the orbit on the vacua. And the second way to see it is using the sigma and tau operations, and they match. So let me give some examples, okay? The first one is SU2, which you already saw. And again, you have a doublet and a singlet. So this one confining vacuum, which is duality invariant. Duality symmetry was not anomalous. And you have a triplet, which means that the triality symmetry is anomalous. You can go to n equal to 3, then you have 4 vacua. And there is also a Coulomb vacuum that I will tell you about after. So for n equal to 3, again, now duality has 2 orbits because there are 4 guys. So it's this and this. So it's anomalous. But the triality has a fixed point, which is C1 in my conventions. So it's not anomalous. There is an SPT which preserves the symmetry. And you can also have this kind of orbit. And then if you go up, you have...
Which partition are each of those guys? 0,
which
1,
what?
and 2. Partitions, 0, 1, and 2.
Ah, okay. No, it's the same partition, just that one partition gives rise to multiple vacua because they are confining vacua. So this is just the partition of 3 into 1 plus 1 plus 1, but it gives you 3 vacua at the quantum level. So I have 1, 0, 1, and 2. And there is the 1 + 2 partition, which has a Coulomb phase, and I tell you something after this example about what you can say.
Okay.
Okay, thanks. And okay, then there is also I just wrote down also the n = 4 table, just to, okay, the last one I wanted to do. And it's always the same game. So this now we have also a 2-2 partition. So this gives rise to 2 vacua more. And you see, you have various orbits, but the new thing is that there is one vacuum, which is both duality and triality invariant. And if you look at what this is, it's a Z2 gauge theory, which can be coupled to a Z4 gauge field, and is both duality and triality invariant. Okay, so this is more like a curiosity. So you find this every time n is a perfect square, there will be a vacuum, which is, if n is k squared, there is a vacuum which is described by a zk gauge theory, and is invariant under the full SL2Zn. So when n is a perfect square, both symmetries are anomaly free. Okay, and let me also state that you can also check. So this symmetry also is a cubic anomaly. It's a bit like a normal zero-form symmetry. So it has a cubic anomaly in 4D, and you can compute it. It's the anomaly for S duality has been computed by Tachikawa, and you just have to add the anomaly for their symmetry and take the discrete part. And if you do the numerology, you can check that when there is an invariant vacuum, the anomaly cancels, because otherwise it would be inconsistent if we have this cubic anomaly, but it's just a comment. Also, before, okay, let me also tell you what happens in the Coulomb vacua. I didn't prepare a slide, but it's very easy. So in the Coulomb vacua, it's known that Maxwell theory also can have duality defects for special value of tau. And it's the same thing. You can gauge the electric one-form symmetry and then do an S-duality transformation in Maxwell. So what happens on the Coulomb vacua is that if you start from tau = I, for example, in the n = 4 theory, you do the n = 1 star deformation, you flow down to the Coulomb vacuum, the gauge coupling is fixed. For example, for SU2, if you start from tau = I, the gauge coupling in the IR is 2 only. Okay. So, and you can also do the more complicated examples in which you have both like Xing, confining, Coulomb, but it goes a bit out of control. But I think the gist is always the same. Okay, and okay, let me notice that there is also like a standard order parameter for this symmetry breaking. So you can just essentially take the derivative of the superpotential, which is the one which people used in the literature. The superpotential has been computed by Dori and Kumar a long time ago for this vacua. So it has some formula using Eisenstein series. And so you compute this derivative, which is this. You go to tau = I. You can verify that it transforms as an order parameter. So the notation is a bit weird here because the one we used in the paper. But this guy is the C1 vacuum, the one which is invariant, and indeed is the order parameter is 0. But in the other two, it changes by a minus sign, so it's like a normal symmetry breaking. And if you go to the triality point, the 3 vacua are related by a cubic root of unity, and the order parameter is non-zero. So it's also like a normal symmetry breaking case in this case. So, okay, and this is consistent with our analysis. So that if you can also show that when you have in general an invariant vacuum, the order parameter vanishes. Okay. Okay, so this concludes, I mean, the part of n = 4. Then I will talk a bit of last 10 minutes or so about n = 1. So if you have questions, I think this is a good point. Okay, so so this is just another example of other thing you can do. Is always the same game if you want. So you did the n = 4. So now we do the second simple example, which is the orbifold. But it will be useful for me to describe the orbifold as a class S theory, just because we know to construct these duality defects in class S. You can also argue for this holographically, but I mean, I have to choose one thing in the talk, so I chose this. So now we think of the orbifold theory as coming from 62,0 by reducing a torus with two regular punctures. So this is just a cartoon of the torus. And the two gauge couplings are related to the distance between the punctures, okay? And there is a duality group, which is just a mapping class group of the torus. So this was classified already by Witt, and then Meiji, Romelsberger, and Warner give all the nice formulas. And it has various generators. So a subgroup is the SL2Z of the torus. So this acts on the on tau in the usual way, but also moves the punctures around, that this test does. And then there are these three transformations which only act on the punctures. So L and L tau essentially translate the puncture in one cycle or in the other. Since we have two, essentially, if you translate both, it's like doing nothing. So there is just one generator. And then there is one which I call S, which exchanges the punctures. And this S is related to cyber duality, if you want. If you had the n equal 1 theory, is related to cyber duality, because if you exchange the order of the things, the gauge coupling becomes negative, and then you cyber dualize to go into a frame where the gauge coupling is positive again. So it's called S, small s. Right? I think of it as cyber duality, although we're n equal to 2, so it doesn't make sense. Okay, and again, this theory has a one-form symmetry, because it's just that in the quiver, the bifundamentals cannot screen the diagonal center symmetry. So the diagonal Wilson lines have a well-defined charge. And now we have to find some duality. So again, we start with S duality, no? This is what we want to use. So S duality changes the global structure as in n equal to 4. And you can see this from the action on the H1 of the torus. Okay? It's the only one which acts on the H1. And the choice of global structure is a choice of a Lagrangian sublattice of H1. So that's how you see it in synthesis. And okay, since S acted on tau, we need to put tau equal to I, so we have a squared torus. But furthermore, this is not enough because the punctures move, no? So we need to put the puncture in some special places and then use some of this transformation which acted only on the punctures to put them back to the right ordering. So in practice, I show you a picture. The thing that you have to do is small s, which is like cyber duality, big S, and this L, which moves the puncture around. And it's like this. So you start with the punctures. This 2 and 1, you can forget about it. So you do S duality. The punctures are, you see, I had to put them on the border because are the only places in which are the same if I rotate the square, essentially. Then the punctures are in the same places, but they are exchanged. So I just move them around until I get to the original configuration. And that's how you find the duality symmetries in all these cases, okay? This is just the simplest one. So we have the sigma transformation, which is just the same thing as the S duality we used in n equal to 4. And we can gauge in our space the one-form symmetry and use sigma. And this is a non-invertible symmetry of the orbifold theory. Same things that we done in the first part. Now we want to look at the deformation that preserves the symmetry. So the first simplest thing to do is that you use a quadratic superpotential with the chirals in the vector multiplet, no? Okay, so you do this. Then you need to know how the duality group acts on these guys, but this has already been worked out for small masses, and this is the action. And now what you want to do is to solve for the you know what is sigma. So you have solved for the masses by imposing that the superpotential goes into itself up to a phase. So it's a bit more complicated, but you solve the equations and there are two solutions. One is that the masses are opposite and the superpotential changes by a sign. And one is the masses are the same and the superpotential gets a I. So we're going to just go with the first one. And you can do the same thing. You take a U1R rotation that is broken by the superpotential, you compose it, and you get a new defect, which is preserved along the LG flow. And, okay, this deformation we are looking at, this is very well-known flow. And in the IR, you integrate out the scalars, and you find the Klebanov-Witten theory with the quartic superpotential. So the claim is that if we move on the conformal manifold of the Klebanov-Witten theory, there is one point in which the Klebanov-Witten theory has a non-invertible symmetry. If you want to find the point, the way to do it is you start from the orbifold, you flow down, and you see where you land. Okay? So for the last 5 minutes, let me also try to understand what is this in the n=1 language, because we have to use S-duality to do the thing, but in n=1 language is not clear what you should do, right? So the claim is that this is in the appropriate definition, because we are strong coupling. This should be a cyber duality on the nodes of the quiver, composed with some discrete gauging. So we couldn't show this, but you can show how it works for the simplest case, which is n=2, because then it's just a SO4, the algebra. So you can use the cyber duality for SO, and it's much easier. So now, if you work out the details, in this SO variable, the superpotential is just the baryon. And the action of cyber duality on SO is known, worked out by Hiroshi Cyber Tachikawa, and is as follows. And you see when an F is equal to 4, is special because the gauge group, the gauge algebra does not change, no? So this is the case in which we are in. We're lucky. And if you have furthermore, it's known that the baryon operator becomes a difference of two kinetic terms. This is kind of important for the details. So then what you do, you start cyber dualizing until you get the right action on the global variance. And okay, we just denote by eta the difference of the two complexified gauge couplings. And our claim is that you can find the same action of the sigma defect by doing this composition of two cyber duality and the shift of the theta, one of the theta angles of the theory. This is a bit, I mean, it's not obvious. We cannot fix what is the action on the couplings, actually. It's not known. But our claim is that in the n=1 language, the symmetry which exists should be thought as a sequence of two SO cyber duality with a shift at theta angle. And you have to compensate it by gauging the one-form symmetry. And okay, intuitively at least, why cyber duality enters the game is quite clear. So usually when you have cyber duality, you don't have one-form symmetry, no? So confining and the X phases are the same. It's not obvious to distinguish them. But what happens is that if you still use the kind of old knowledge, you see that in the cyber dual frame, an X vacuum becomes a confined vacuum. Now, when you add the one-form symmetry, what happens is that it just becomes a physical information. And for the thing to be consistent, it must be that what condenses in the X vacuum, which is a Wilson line, is mapped to something which condenses in a confined vacuum, which is a Toft line or a diamond. So it must be some non-trivial action on global variance. Although we couldn't work out precisely in this paper in general how it works. But I believe this should be the correct answer. Okay, so let me wrap up, so then you can take questions. So today I want to describe how these non-invertible symmetries can be preserved under some for DRG flows. And I described a bit some of the implications for gapped phases, but didn't describe any result for the gapless phases. So you can extend this for more general Quiver theories. You can extend this if you do things from class S in different ways. I think it's possible, but most of the results are, I mean, I don't know what to say afterwards. I know that the symmetries are there, but I don't know what to do with them. And another thing which I think is nicer is to study RG flows which preserve duality but break SUSY. So for example, for n=4, you can turn on the Konishi operator. And this preserves the duality symmetry but breaks SUSY completely. Or you can turn on like the 20 prime, some components, and it's a similar story. And these are relevant deformations, and they flow to some I mean, the 20 prime is a bit is not so interesting, but the Konishi flows to some interesting gapless phase. So it would be nice to put some constraint of this non-supersymmetric CFT. So this I'm currently working on. And then presumably you can do the same thing also in the other examples. It's just that it's not clear what the correct tools are to attack the problem. So I think this is an open problem still. And okay, so thank you. And now I can take some questions if you want.
All right, let's thank Christian. And I guess, yeah, we will now all turn to duality preserving our G-flows. Do we have questions? People are still a little shy. What do you mean when you said just now the conclusion that there are symmetries, but you don't know what to do with them for the class S case?
It's just that, so most of these flows are between CFTs, no?
Yeah.
So I don't know how to constrain the CFTs, how this discrete symmetry, because this is some kind of discrete symmetry, constrains CFTs. I know how it constrains gapped flows, so gap phase, but I don't know. So you know it's there, but you don't know what to do with it.
I see. Okay.
So technically, it's possible to prove that these exist in various cases, but I think it's more important to understand if they have any strong impact on helping you to understand the strongly coupled theories, no? Because they might not. So I think that's an important question.
Very good. Do you have more questions? Okay, then I'd say let's thank Christian again. And
Thank you.
we can go off the record.